If you're fine-tuning a large reasoning model today using standard supervised methods, there's actually a 92% chance you are completely bulldozing its foundational geometry without even knowing it. This is AI paper slop, and today we're jumping right into On the Geometry of On-Policy Distillation by researchers from HKUST, UT Austin, and a few others.
Yeah, quite a lineup.
Right. So quick summary of the core insights for you all before we get into the weeds. On-Policy Distillation, or OPD, it's not just some, convenient midpoint between supervised fine-tuning and reinforcement learning.
No, not at all.
It actually carves out its own completely distinct parameter space geometry. The authors call it a relaxed off-principle regime. And dynamically, OPD experiences this thing called early subspace locking. It rapidly finds a low-dimensional update channel that is functionally sufficient for training, and it just stays there.
Exactly. It locks in.
Yeah, and crucially for your next training run, this lock is incredibly robust to token sparsification and off-policy sampling, but it will instantly break if you mess with the composition of your training objective.
It's honestly a phenomenal paper because it completely shifts how we need to think about post-training.
Yeah.
We've spent so much time, analyzing when OPD works behaviorally.
Right, we know it's great for complex reasoning.
Exactly. We know it works. But its actual optimization dynamics in the parameter space have been this total black box. We are finally moving past just staring at evaluation loss curves and trying to understand the actual physics of the weights themselves.
Well, that actually brings up a good point, because I can hear the skeptics already.
Oh, for sure.
If you're an ML engineer and you run an optimization and your AIM math benchmark score goes up, why on earth should you care what the weights look like geometrically?
Right, line goes down, model good.
Exactly. If the loss is going down, isn't weight geometry just sort of an academic curiosity?
Not at all. And thinking that way is exactly how you end up with a model that, catastrophically forgets how to speak English just because you taught it Python.
Oh, wow. Yeah.
Because the way your weights move dictates the model's stability and its ability to generalize. When you only look at evil loss, you're just looking at a symptom. Weight geometry is the underlying physiology.
Right.
Pre-trained models have a really highly specific dominant spectral structure. It's basically their foundational brain. If you know your training method is massively distorting that structure, you are risking permanent damage to its core capabilities.
Okay, so understanding geometry tells you how to actually steer the optimization. Rather than just, crossing your fingers and praying, the loss curve doesn't suddenly spike.
Exactly.
Okay, that makes it very real for anyone actually deploying these things. You need to know if you're quietly lobotomizing your model to get a higher math score.
Mm-hmm.
So let's look at the current post-training landscape to see where OPD actually sits.
Yeah, let's lay it out.
Conceptually, if you're trying to post-train a large reasoning model, you basically have three tools. You have Supervised Fine-Tuning, SFT, which relies on dense offline demonstrations. SFT is basically an unconstrained bulldozer reshaping the whole landscape.
That's a great way to put it.
Then you have reinforcement learning with Verifiable Rewards, RLVR, which uses incredibly sparse sequence-level outcome signals. It's like a binary 1 or 0, right?
Right, depending on if the math answer was just right or wrong. It's more of a precision scalpel.
The scalpel, yeah.
Oh.
And finally, we have OPD, which is this weird hybrid. You are training a student model on its own generated trajectories, but you're providing dense token-level guidance from a stronger, usually much larger teacher.
Yeah.
We're trying to figure out what tool OPD actually is.
Right, and to figure out what OPD is doing under the hood, the researchers had to set up a really controlled environment. They couldn't just, compare random checkpoints from different runs. Yeah. So they used a Qwen3-8B base model with an SFT anchor, evaluating specifically on AIME 2024. They made sure the SFT anchor and prompt distribution were identical across the board.
So any geometric differences were purely the result of the algorithms themselves.
Exactly. And they deployed 4 specific parameter space diagnostics to map this out.
Okay, let's get into those diagnostics because this gets fascinating. Starting with bfloat16 aware update sparsity. Now, I know bfloat16 is the standard precision for these runs, but why are we explicitly looking at sparsity through the lens of bfloat16? What's the physical mechanism there?
It really just comes down to hardware reality. B-flat 16 has a heavily truncated mantissa compared to FP32. It represents a wide range of numbers, but with very low precision.
Right.
Because of this, tiny micro updates to the weights simply get absorbed by rounding errors. They literally just vanish.
Oh, I see.
Yeah, a weight only structurally changes in a way that actually affects the forward pass if the gradient update is mathematically large enough to cross that B-float 16 precision threshold.
So it's effectively a physical filter for whether an update actually matters at all.
Exactly. And when you look through that filter, the numbers are kind of shocking. Under SFT, only 8.1% of the weights remain unchanged.
Wait, I really need to pause on that. SFT literally overwrites nearly 92% of the model's weights in B-float 16.
Yeah, paves right over them.
That is insane. Like I said, it really is an unconstrained bulldozer.
It's pure brute force. But contrast that with RLVR. RLVR is highly conservative. It leaves 77.2% of the weights completely unchanged.
Okay, so a very sparse subset gets tweaked.
Right. So the core question was, where does OTD land?
Well, since OPD uses dense token supervision just like SFT, you'd intuitively expect it to be closer to the bulldozer, right?
Mm-hmm.
Because it's getting feedback on every token.
You would think so, but it actually lands right in the middle. OPD leaves 51.6% of the weights unchanged.
Huh.
And what's wild is how robust that number is. I mean, you can scale the teacher model from 8 billion parameters up to 32 billion.
Yeah.
You can switch the domain from math reasoning to code generation. Yeah, you can even use a sparse mixture of experts teacher. That 50-ish% sparsity holds completely stable.
That is remarkably consistent. Now, the second and third diagnostics looked at principal angle rotation and spectral drift. And for anyone rusty on their linear algebra, we are basically asking, how much are you warping the core highest variance directions of the pre-trained model?
Exactly. They looked at the dominant singular subspaces, which are the highest curvature directions in the parameter space, and SFT significantly distorts these directions.
How much?
Its principal angles shift by more than 10 degrees, which means you are physically rotating the foundational structure of the network.
Wow.
Meanwhile, RLVR barely touches them, shifting less than half a degree.
And OPD?
OPD sits right around 1 degree. So OPD causes some slight rotation, but fundamentally it preserves the pre-trained geometry.
And their final static metric was update mass overlap, right?
Yeah.
Because they wanted to see exactly where these visible updates were physically landing.
Yes, and this is where the off-principle part of the author's framework comes in. SFT updates heavily overlap with the principal high-magnitude weights. It basically attacks the core structure.
Right.
RLVR actively avoids those high-curvature regions, shifting its updates toward low-magnitude weights. And OPD actually follows RLVR's lead here. It aggressively shifts its updates away from the principal weights and pushes them into the low magnitude regions.
Just like slightly less strictly than RLVR does.
Exactly.
Okay, so if we synthesize all of that, OPD is more selective and geometry preserving than SFT, but it's less constrained than RLVR. So that's our relaxed off-principle regime.
Yep, you got it.
But I have a major mathematical problem with this.
Oh, what is it?
Well, if OPD has dense token-level supervision, meaning the teacher is providing a distinct corrective signal on every single token, why isn't it acting like a bulldozer? The math just doesn't seem to add up there. What is physically holding it back from tearing up the principal weights like SFT does?
That is the exact paradox the authors wanted to solve. And it brings us to what they call the three-gate optimization view.
Okay.
To understand why OPD is restrained, despite having dense signals, you have to look at 3 consecutive filters that an update must survive before it becomes a permanent structural change.
Okay, I'm tracking. Let's walk through these gates. What is gate I?
Gate I is the KL anchor. Unlike SFT, which just, blindly optimizes offline cross-entropy against a fixed data set, OPD operates on policy. It utilizes a callback labeler or KL divergence constraint against a reference model.
So it's anchoring the update.
Right. It anchors the update to a local quadratic budget.
So you're saying the KL constraint acts like a physical leash. It literally caps how far the model can wander from its current state in any given step.
Yes, it's an incredibly strict leash. SFT doesn't have this leash, which is why it can freely overwrite 92% of the model.
Makes sense.
But because OPD is leashed by gate buzz, it is forced into gate 2, the model geometry itself.
Wait, how does the geometry act as a gate?
Well, because the step size is strictly bounded, the optimization landscape naturally steers these bounded updates away from the high curvature principal directions.
Why does it steer away, though?
Think about it like hiking. If you are on a very short leash, You can't afford the energy to climb straight up a massive, steep mountain. The mountain represents those high curvature principal directions.
Oh, you see.
You are forced to take the path of least resistance, which means walking along the flat valleys. The optimizer naturally drifts into the off-principal, low-curvature directions because it just doesn't have the budget to climb the principal hills.
That's a great analogy.
Yeah.
And that leads us directly to gate D3rd, which is the precision realization we discussed earlier with bfloat 16.
Exactly.
If you're walking in those flat valleys, taking tiny steps, a lot of those micro updates are just going to get swallowed by the rounding error.
Yes, exactly. So those three gates explain why OPD is off-principle. But you ask why it's a relaxed off-principle regime compared to RLVR. Like, why does it update 48% of the model while RLVR only updates 22%?
Right, because if they both have the leash, why does OPD manage to alter so much more of the landscape?
It's because of the dense heterogeneous token signals. In RLVR, your feedback is a single scalar signal for the entire sequence.
Like a broad +1 or -1?
Right. That is a very narrow directional pull. You're basically pulling against the leash in exactly one direction. But in OPD, you have a distinct coefficient for every single token based on the teacher-student disagreement.
Oh.
Yeah, so you are pulling against the leash in hundreds of different directions simultaneously. This denser signal broadens the accessible directions in the parameter space, pushing far more coordinates past that bfloat 16 threshold in gate 3.
That perfectly bridges the gap. So it's not removing the leash, it's just straining against it from far more angles simultaneously.
Precisely.
Now, everything we've talked about so far is the static picture, right? The endpoints. But training is a dynamic journey over thousands of steps. How do these updates actually evolve over time? Because this leads to what I consider the paper's most incredible discovery, subspace locking.
Oh, this completely upends how we think about the life cycle of a training run. The researchers tracked the cumulative updates across checkpoints using a metric called stable rank.
Real quick, if you're wondering what stable rank actually means in practice, think of it as a measure of how wide or dimensional your update channel is.
Right.
If you have a high stable rank, your updates are scattered across many different mathematical dimensions. Low stable rank means your updates are highly concentrated.
Yeah, and when you map the stable rank trajectories of these three methods over time, they are radically different. SFT's stable rank just keeps growing.
Like it's spreading out.
Exactly. As training progresses, it constantly expands its update subspace, frantically finding new directions to alter and memorize. RLVR does the opposite. It starts somewhat diffuse and then aggressively contracts toward a low-dimensional endpoint.
And what about OPD?
OPD enters a narrow, incredibly low-dimensional band almost immediately, literally within the first 20% of the training process. And it just stays there. Its stable rank is completely flat for the remainder of the run. It locks into a specific geometric subspace and never leaves.
Okay, I'm going to play devil's advocate here for a second, because if I saw a perfectly flat, stable rank curve, my first thought wouldn't be, oh, subspace locking.
What would it be?
My first thought would be that the optimizer just died. Like, are we sure the stable rank isn't just low because OPD stopped taking meaningful steps? If the updates are tiny, the dimension looks low.
The authors anticipated exactly that critique, and they dismantled it using the Frobenius norm. They didn't just measure the dimensionality of the update, they measured the actual accumulated magnitude, the raw energy of the movement.
And what did that show?
It showed that OPD accumulates a substantially larger update norm than RLVR, yet it maintains a comparable, completely flat, stable rank. So the optimizer hasn't died at all.
Okay, so it's moving a lot.
It is moving a massive amount of weight mass, but it is exclusively moving it down a very narrow lock channel.
Okay, so grounding this in a visual for everyone, it sounds like SFT is basically a driver swerving erratically all over a multi-lane highway, constantly changing lanes to pick up new information.
Not like that.
RLVR is slowly and carefully merging into the carpool lane. But OPD just locks onto a monorail track on day one and accelerates massive amounts of cargo straight down that single rail until the end of the line.
That is a brilliant way to conceptualize it. It finds the exact track it needs, and the geometry restricts it from ever derailing.
Which naturally leads me to ask, is that monorail track actually functional? Like, it's fascinating that OPD finds a track early on, but if you theoretically clipped off the rest of the parameter space, would the model instantly collapse? That brings us to the rank 16 bottleneck experiment, which honestly blew my mind.
This is where the paper transitions from a great observational study to a profound structural revelation about how large language models actually reason.
Yeah.
The researchers took the top 16 singular subspace of the OPD update channel just 20% into the training process.
Just to emphasize, we are talking about models with billions of parameters living in massive high-dimensional spaces, and they isolated just rank 16.
Exactly, just 16 dimensions. And then they constrained all subsequent gradient updates for the entire rest of the training run strictly to this early rank 16 subspace.
That's wild.
They mathematically projected every single gradient back onto these 16 dimensions. They forced the model to stay on that exact monorail track.
And the results? Did it cripple the model's ability to learn complex math?
Not at all. OPD's performance on the AME 2024 math benchmark, as well as other brutal reasoning benchmarks like Minerva and AMC, was completely preserved.
Unbelievable.
It performed functionally identical to the unconstrained baseline.
That is staggering. So you're telling me that by the 20% mark, OPD has already mapped out the precise 16 dimensions it requires to learn highly complex mathematical logic, and the millions of other dimensions in the parameter space are basically just noise for the rest of the run.
For OPD, yes, that early subspace is functionally sufficient. But here's the crucial counter-experiment. They tried applying this exact same rank 16 bottleneck to SFT at the 20% mark.
And I'm guessing the SFT bulldozer crashed immediately.
Hard crash. SFT's performance substantially degraded. And understanding why is the key to this whole paper. SFT fundamentally learns by rote memorization. It requires vast, constantly expanding parameter space to store those dense offline demonstrations.
So it needs the space.
Right. If you choke SFT down to 16 dimensions, it physically runs out of room to store that memory. OPD, conversely, is not memorizing answers. It is learning a generalized reasoning path.
And a logical rule is vastly lighter to store than 1,000 memorized textbook answers.
Exactly, which is why OPD only needs those 16 dimensions to thrive.
Okay, if this rank 16 lock is the secret to OPD's incredible efficiency and reasoning power, the immediate million-dollar question for any ML engineer listening right now is, how do I control it? If I'm writing the training pipeline, what maintains this lock and what breaks it?
The researchers extensively tested this. They wanted to know the boundary conditions of the lock, so they introduced 3 distinct perturbations.
What was the first one?
First, they looked at token sparsification. They tried keeping only the top KL tokens, the specific tokens where the student and teacher had the highest divergence. They also tried randomly keeping just 50% or even randomly dropping 75% at the tokens entirely.
Did that derail the train?
Not even slightly. The lock remained perfectly intact. The stable rank trajectory barely flinched. Changing the density or the specific selection of the supervision didn't change the underlying geometry.
Okay, what about the rollout policy? Because in standard OPD, the student generates the text and the teacher grades it. What if you force off-policy rollouts where the teacher generates the text and the student learns from tracking the teacher's trajectory?
Again, the lock remained intact.
Really?
Yeah. The update norm got marginally larger because the student had to stretch a bit further to reach the teacher's trajectory, but the spectral shape, the monorail track, didn't change at all.
So if runtime perturbations, like radically changing the data you feed it or randomly dropping a massive amount of tokens, don't alter the geometry, what does? What actually fractures the lock?
Objective composition.
Yeah.
The researchers interpolated the standard OPD advantage signal with an RLVR advantage signal. Basically, they mixed the math accuracy sequence level reward with the token level teacher correction.
Okay, mixing the signals.
Right, they used a mixing parameter, alpha. As long as the OPD signal was dominant, the lock held. But the moment the OPD signal became too weak, when alpha dropped to 0.05 or 0.01, the trajectory violently broke out of the locked regime.
So it just lost the track.
Completely. It rapidly expanded into a totally new high-dimensional spectral space.
So the objective composition is basically the steering wheel here. If you mess with the token sampling, the car keeps driving straight. But the second you change the objective, you yank the wheel into a completely different geometric space. Why does the math work that way?
Because of how the gradient is physically constructed, the gradient in OPD can be understood mathematically as a sum over the sequence. For every token, you multiply the local Jacobian, which maps out the sensitivity of your model's outputs to its weights by the teacher-student discrepancy.
Right, just basic chain rule.
Exactly. When you randomly drop tokens or change who generated the text, you are just masking out specific terms in that sum or slightly altering the weighting. You fundamentally preserve the dominant covariance geometry of the Jacobian.
I see.
But when you mix in a completely different objective signal, like an RLVR sequence-level reward, you are fundamentally changing the underlying gradient vector itself. You alter the core mathematical objective, which fractures the covariance matrix, and the lock shatters.
That brings this whole thing into such sharp focus. We've gone incredibly deep here, but let's synthesize this for the ML practitioners tuning in. Based on all of this, what is the ultimate takeaway? How should this change how you write your code tomorrow?
The absolute most critical takeaway is that you have to stop treating OPD simply as RLVR, but with denser tokens. It is a fundamentally different geometric beast.
Right.
If you are designing future post-training algorithms, your entire paradigm needs to shift toward geometry control. You should be actively computing the singular value decomposition of your update channels and monitoring the stable rank during your training runs.
Stop flying blind, basically.
Exactly. If you see the stable rank starting to wildly drift or expand, you cannot fix it by tweaking your data sampling or dropping tokens. You have to fix it by adjusting your objective composition. That is your primary and really only lever for maintaining stability and preventing catastrophic forgetting.
It's a complete shift from data-centric tweaking to geometry-centric steering. And that leads me to a final, slightly provocative thought to leave you all with.
Let's hear it.
If a large reasoning model only truly needs a rank 16 subspace to master complex reasoning via OPD, and it maps out this subspace in the very first 20% of training, could future algorithms analytically predict or pre-calculate these low-dimensional channels before the optimization even begins?
Oh, that would be something.
Right. Could we effectively bypass the massively expensive, compute-heavy, full-parameter search entirely? It is definitely something to ponder as you go back to your codebase and fire up your next cluster. Thanks for joining us for this deep dive on AI paper slop. We'll catch you on the next one.